This?
No. Yeah, you could use. Okay.
All right. Good evening, everybody. Thank you for still being here today. Well, my name is Nicolas Volet. I'm from Medico, Denmark, and I have here in this box Far-UVC laser. I'm not a magician. I'm a laser physicist, and I welcome anybody that would like to come and talk to us and have a look at what's inside this box, maybe after the talk or later tomorrow. So I keep it here with me all the time. All right, maybe to start with some geography. We are based in a city called Aarhus, and I summarize on this slide the extent of my knowledge of the Danish language. I'm originally from Switzerland. That the double A in Danish is pronounced like an O, right? That's right. So Aarhus is a city of about this size. This is the second city of Denmark after Copenhagen. And basically a good 10–20% of the city is filled with students. So it's a very nice town to work with. And also very talented students that is very nice to then attract to our company to work with. All right, so this is the outline of my talk. I have 5 pillars here that I will briefly go through. I do acknowledge this is the end of the afternoon, and I have a serious jet lag. It's about midnight for me, so I go briefly to this. I'd like to acknowledge these 3 associations that we are a very proud member of, and also to thank the organizer of this workshop. This is a fantastic venue to come. And also acknowledge strong partnerships with Ushio that we really enjoy working with. All right, so maybe a little bit of polemic on what Far-UVC is. There are a few definitions here on whether it ends at 230 to 35, whether we should go down to 200, or if it gets dangerous because of ozone and other things. What we're really also interested about with this laser technology is basically what we call deep UV. And deep UV is maybe simpler definition, anything below 250 nanometers, right? So it englobes safe deactivation of pathogens, but also other applications, Raman spectroscopy, communications in the solar blind spectrum, lithography, and I put here as etc. Other applications that we can talk about. This is, I have a double hat. I'm also a research professor at Aarhus University, and this is my team. I'm showing this picture because Medico was born out of COVID-19, but also out of a few of these ladies and gentlemen, in particular Emil, my PhD student, which is a co-founder of Medico. What we do is photonic integrated circuits, basically chips based on silicon or other semiconductors that already exist. We don't invent new materials. What we do is make building blocks out of these chips, and in particular in this chip that you can see over here, it's the size of a centimeter. You have not 1 laser, but 10 lasers on each side of the chip. And then we integrate this into other structure, detectors, waveguide, and so on to make real-life devices. So we are working down from the design up to the prototyping of photonic integrated circuits in a way that is compatible. So I highlighted here in yellow because I don't want to go through the whole slide. It's compatible with high volume production capability. And that's what also we are looking for at Medico, to develop technologies that are available today. And we're very excited to hear about what's going to happen in 5–10 years. We'll keep an eye on that, but we want a laser here and now in the Far-UVC. So we also work on with the fabless approach, meaning that we don't fabricate anything. We focus on IP design, and then we send for fabrications with some partners, some foundries, depending on the material system that we work with, that have already developed these technologies for this past 5, 10, 20, 30 years. We characterize these technologies in-house, and then circle back different iteration cycles. So here I'm just showing what it looks like, these chips. This is a mask design that we would do, which is typically a plug and play of different components, photonic and electronic components, that we send to a foundry that eventually returns to us something like that. And then we characterize these structures. Each line here is a different waveguide that we characterize with a laser that we couple on the side and measure how the chip actually influences the light as it propagates through. We've been working for quite several years now in improving lasers at much longer wavelengths, 1550 nanometers for telecommunication industry. Got some success of commercializing lasers with this company, Fabless, with the prospect also of not making just a laser, but then playing with the frequency of light as it propagates through a chip, making something that is called a frequency comms. And each out of one laser line, what we're really up to is create more and more laser light on one chip. So eventually, yes, make a laser, but then makes maybe 10, 20, 100 lasers on the same chip. This, you know very well, this slide. So we try to then use this, not this technology, but this background to then implement a laser in the Far-UVC. You're well aware of this technology of excimer lamp that we sell at Medico. I will maybe skip a few slides here. We've developed different designs for different applications, entering also pharma industry, and with different either venues, also partnering with some sports team. In particular, we've been present already at the Olympic Games last year, where our devices were installed in dressing room and so on. Half of our people are half of the people is scientists, and maybe the other half is, we call them superheroes, entrepreneurs and policymakers. We have strong presence in Europe. Again, we are based in Denmark, southern part of Africa, Southeast Asia, and now starting to come to this continent as well. So maybe for the next 5 minutes, I would like to talk a little bit more of laser diodes and then show you some properties of this laser that I have under my elbow, right? First of all, what's a laser? Well, it's an acronym for this stimulated emission, which is a very special type of light made of identical photons. What it means that we can create a very narrow spectrum. And after a few years working with lasers and photonics, you make this type of jokes. All right, what's a diode? Well, everybody would know what a diode is, but for us, what is a diode is something that you can make on a chip. And basically, summarizing this slide in one word, what's a laser diode is something that reduces the swap. What's the swap? Reducing size, weight, operating power. That's what we're up to. Making it smaller, more power efficient, and converting a spectrum that looks like that for excimer technology to something that looks much narrower. So this is a measurement that we've done with the laser that we have over here. It's basically monochromatic, meaning it's not broadband. And on top of this, you can tune the wavelengths by tuning some property of the materials, as Leo was mentioning a few talks ago. This is the extent of my knowledge of quantum mechanics. Basically, it shows that you can generate light by playing with the properties of the atoms, and you can also play with the absorption and so on. This was one of the favorite books of my daughter. Now she's 6 years old. She's a bit too old for that, so I'll skip it. Basically, what's happening with the light matter interaction, this is a huge topic, and I have a couple of slides on this. There are a few things that can happen that matters when we make a laser. First of all, absorption. We want to avoid absorption. This is hitting the devices, and this is very bad because you lose the light, you lose the photon. Next thing that can happen, that you want to happen, is dispersion. You have light coming in, it excites the material for a short period, light going out. And this is responsible for the refractive index of light. And we use this in laser technology to confine the light, to guide the light on a chip. Scattering, something bad, it's a complicated word. What it is, similar to dispersion, but the output light then has a different direction. This is bad, especially when you go to shorter wavelengths, because light is not guided anymore, it goes away from the chip, and therefore it is also lost. And eventually, a little bit of magic, it's called wavelength conversion, part of nonlinear optics. You have light in, excites the material, and then more light in. For instance, with a laser, it continues to excite the material. And guess what can happen after that? while there's light out, but at different wavelengths. And that's what we're up to over here, starting with a blue laser and then converting it to Far-UVC. All right, so this is not science fiction. This is a very old picture that I took from a textbook from the 60s, already back in the 60s. People were studying how to change the color of laser light with something called non-linear crystals. What we are up to is to, of course, reduce drastically the size of this setup to make it on a chip. And this is a recent result that we obtained to make laser not in the deep UV, but we're also up to the other side of the spectrum. Here is our result that were published for making a laser at 2.3 micron, so in the mid-infrared. And you see from these animations how the photons are being basically converted, guided on chip based on silicon, and then converting to different wavelengths of interest. The physics is insanely complicated, and I just put this slide for those that would be interested, that there is some physics behind it. And of course, I don't have any time to go through any of these interesting things, but the point is that you need to masterize mode profiles, how lights actually interact with materials, in order to what? In order to extract the conversion efficiency, what we are all about. Example of where nonlinear optics, wavelength conversion has been used for a long time is to make a green laser pointer. This is an example I took where the laser over here is basically in the near infrared and the output is in the green. Funny thing, for green laser pointer, they also care about filter to block unwanted longer wavelengths. And why we care about a blue laser diode? Well, that's because they exist. They have been developed for many years by this gentleman and a few others. This was the topic of a Nobel Prize even for the LEDs, not even the lasers, back in 2014. And we are in particular interested in 445 and other wavelengths nearby to then double the frequency or divide by 2 the wavelengths and generates this into Far-UVC. I showed this slide this morning to a seminar at Columbia University in the laser department, because this is something that has been done here at Columbia University, where researchers have been using laser diode. Again, it's a chip that is about 1 or 2 millimeters in size, and then converting the spectrum of the laser, which is not necessarily monochromatic, into something that looks much nicer. How they did this? By actually designing not a frequency converter, but a chip based on silicon to stabilize this. This is a technology that involves guiding light and creating functionalities of light as it propagates on a chip, highlighted in yellow. And then moving to industry, this is an example of a company in Switzerland that makes this type of technology to stabilize the light for quantum applications, quantum photonics. What we're up to is this type of cartoon, which again is in this box over here, which generates a laser light. In this example, we were up to about 222 nanometers. But what we demonstrated is laser down to 202 nanometers, so at the border of the Far-UVC, and up to 237, starting from other blue laser diodes that are available at twice these wavelengths. And the device is resistant of a broad temperature, and I heard resistance to our salespeople that brought it from Denmark, and it's still in one piece. An example, just a comparison between excimer technology, excimer spectrum, and a blue laser, again showing that it is much narrower bands, and there's no problem of longer wavelengths, whether it's longer than 230 or 235, we can just tune the wavelengths that way. This is more for the physicists of this audience, showing that the spectrum is also tunable, meaning that you can change the wavelengths, and also that it depends, the output depends essentially with the square of the input power. This is a clear signature that it is indeed a non-linear process. And maybe I end with this slide, which is not a conclusion, it's maybe towards the future, where we then started to see what else can we do out of this. What if we actually start with 2 blue lasers at different wavelengths? Each of them actually converts very efficiently to the Far-UVC, and okay, maybe beyond the Far-UVC. But very interestingly, you can also create more and more wavelengths, more and more peaks, very narrow peaks in the deep UV via this phenomena of some frequency generations. So it is actually a broadband frequency converter, broadband in terms of frequency, that we have demonstrated. Thank you very much for your attention.